In this video, I'm going to talk about the chi-square distribution and the goodness of fit test that uses the chi-square distribution. So first, let's see what we can do with the chi-square goodness of fit test. So let's say we want to see if we have a fair die. So if we have a fair die that has 6 sides, then you'd expect to see each side, if you were rolling this die, about 1/6 of the time. So of course that's not going to be exactly 1/6 if you do 20 rolls. If you do 100 rolls, you'll probably get better and better and closer to that 1/6 mark per side. And then if you could do 1,000 rolls, 1,000,000 rolls, eventually you'd get really close, and then perfectly 1/6 of the time you would see each side of the dice. But let's say that we had 36 rolls of a die, and so we'll have the different sides of the die that are labeled 1, 2, 3, 4, 5, and 6. And we would expect to see each side 1/6 of the time. So I'll write out 1/6. So then as a percentage, we would then figure out 1 divided by 6. So let's go ahead and do that. 1 divided by 6, so that's about 16.7%. So each proportion here, 0.167 if we go out to 3 decimal places. So each one of these is a 167. Now I want to see those decimals because then I will end up multiplying my sample size. So n equals 36. I end up multiplying my sample size by these proportions for any goodness of fit test. And we'll see about that later on in another example. So in this little table that I've been writing here, we have the different sides. We have what we expect to see if we have a fair die. But then we have data that we collect. So we roll the die 36 times, and this is what we observe. We observe that we saw the 1 5 times. And then the 2, we saw that happen 7 times. The 3 happened only twice. The 4 happened 10 times. Then there's the 5, we saw that 6 times. And then there's one more number, the 6, and that's going to fill out the rest here. So I was actually just making up these numbers here, and I need to make sure that all of these numbers will add up to 36 because they're my observed data. And if my sample size is 36, then I have to make sure that all these numbers add up to 36. So let's see, I have 12 already, 5 and 7, and then I have a 2 and a 10, so that's another 12. And then I had a 6. So far, we're at 24, we're at 30, and because again I'm making up these data, I just need to make sure that I got the right number in the last place. That means I saw the 6 happen 6 times. So you'll notice that these numbers sort of fluctuated, but we need to figure out if they fluctuated too much from the 1/6 proportion, or if there's a little bit of wiggle to make sense that, yeah, the observed counts are going to vary because we're gathering real data, but it's still within kind of a usual bound. Our goodness of fit test is going to compare these observed counts. So it's going to compare observed counts against what we expect to see. So I'm going to make another row here. These are the expected counts. So the reason why I want expected counts is that I can't compare a 0.167 proportion against a 5. You know, those numbers are really different and they don't make sense because they're the wrong units. One of them is a percent, the other one is a count. So what I'd end up doing is taking these expected proportions and turn them into expected counts. And you do that by taking n, your sample size, and multiplying it by p, your proportion. So in this case, our sample size was 36, and I'm going to multiply it by all of my proportions up here, p, to get what I expect to see if this proportion of 1/6 everywhere is true. Then what should I get for my count down here? So I'm going to take 36 and multiply it by p. So I have 1/6 in the side of 1. I have 1/6 in the side 2. Or you could round it out to the 0.167. But really, I'm going to be taking 36. And because all the proportions are the same, 36 times 1/6, and I end up with 6. So it kind of makes sense. If all of the categories are equal in count, then that means I should be getting, equal in proportion, then I should be getting equal counts in all those categories. So when we end up going through the goodness of fit test, you're comparing 5 against 6 and saying, is that close or far away? 7 against 6, close or far away? 2 versus 6, 10 versus 6, 6 versus 6, 6 versus 6, and looking everything all at once and coming up with an answer, which is then the result of our goodness of fit test. So you can kind of think of this as how good does our data fit the expected proportions. Now, different problems will give you different proportions. This example happens to have all equal proportions, but in some categories, you only have decimals. They give you 2%, 5%, 10%, and it better all add up to 100%. The main idea is the same though. You'll always multiply n times p. Sometimes you just have to put more work into it because all the little p's change. In our case, they were the same, so I only had to do one step. All right, so in another video, we'll look at critical values and p-values for the chi-square distribution. In this video, I'm going to talk about critical values and p-values and how to find them on a chi-square distribution. So I'll have two examples here. One is about a critical value and how to find it, and then the second example is a p-value and how to find it. So to use Statcrunch, I have a Statcrunch window open up here. We're going to use the chi-square calculator. So we'll find that by going to Stat, Calculators, and then down to chi-square. So the way this calculator works is there's two options. You can do the standard way, so it's grayed out here, or if you do a between, this would be useful if you have a two-sided test, but that doesn't apply to us in this chapter, so we're just going to do standard. So you'll notice that this distribution is right skewed, and the larger your degrees of freedom are, DF, then the more this graph shifts to the right. So if I put in degrees of freedom of 60 and pushed compute, you can see that that looks more normal now. What we'll be doing is typing in our degrees of freedom and then filling in either this box or this box and then computing an answer. So let's go back over to what I was going to use as an example. So let's say you want to find a critical value. You're doing a goodness of fit test and you need to have a critical value so you can make a conclusion to your test. So we are starting off with a significance level of 0.01. I just made it up, but you'll be given that in the problem. And the number of categories in your goodness of fit test is 6. Let's just say we need to compute the degrees of freedom. Now, we've seen degrees of freedom before, and that was with a t-distribution. But in a chi-square distribution, we have a different way of computing degrees of freedom. We call it categories, and then subtract 1. So, kind of the same process as your one-sample t-test, but we're calling them categories. So we'll take 6 minus 1, and so we have 5 degrees of freedom. So if I need a critical value for this goodness of fit test, we've learned that the goodness of fit test is always right-tailed. So here's my distribution. The p-value is the area in the right tail, so that right tail area is 0.01. And this chi-square cutoff right here, that's what we need to find out. We need to know how far over from 0 do we need to go so that anything beyond that chi-square value is the reject region. And we have to have 5 degrees of freedom. So if you change your degrees of freedom, then it actually changes the shape of your graph like I showed you, and so then your critical value would change. So let's go over to Statcrunch, and we have degrees of freedom here of 5, so 6 minus 1. And we need to find the chi-square value. So we're going to take that number out, change the symbol to greater than or equal to, because x greater than some amount is going to be the area in the tail. So that area in the tail is 0.01. We have a right side. It's not the end of the world if you leave the arrow going the other direction. It just means that you'll be finding the wrong side, and you'll see it by the picture because it doesn't match what we graphed, and you'll know to flip it. So let's push compute. And here we go. So our nice right skewed chi-square distribution. This red area is our 1%. And then this cutoff is a little bit over 15. So the critical value is 15 point, let's say, 086. 15.086. So this is our critical value. You'll notice that the scale is wildly different than what we saw with the normal and the t-distribution. It's none of this -3 to +3 business. The chi-square values go from 0 up into the 20s, 30s, 50s, all depending on what your degrees of freedom are. So in this case, any chi-square value that is 15.086 or larger would cause us to reject our null hypothesis. So let's do the opposite, and let's say you need to compute a p-value. So you are given the test statistic, and you have your number of categories, so we'll need to compute the degrees of freedom. So just like we did before, we'll take 4 minus 1, so we have 3 degrees of freedom. Now this is where we fill in the other part of the box. We're going to put in 3 degrees of freedom, and I want to find the area in the right tail, because p-values for the chi-square goodness of fit test are always on the right side, so keep the greater than or equal to sign. And now I need to put in what my critical value was. So that was 32.5. 32.5. All right. And this area in the tail, that's what we're going to get when we push compute. So here I pushed enter already, but you notice that there's no red showing up, and that makes sense because the area in the tail is crazy tiny. Look at how many decimal places with zeros that is. So we're talking 4.1 times 10 to the -2, 4, 6, 7th. 4.1 times 10 to the -7th, which is basically 0 when you round it out. So this number line, it stops at 20, and we're all the way over at 32. Makes sense that we have a very small p-value. So if the p-value is low, h0 must go. We'd end up rejecting our null hypothesis for this example test that we're conducting. Let's say that our test statistic, let's say that it's 6.8. I'm just making up numbers again to show you a different answer. If our test statistic was 6.8, the red area is our p-value, and then in this case, we would have a p-value of 0.0786. So you'd have to know what your level of significance is to decide if you're rejecting or not rejecting your test, but this is how you would compute your p-value for a chi-square test. And both of these steps that I showed you, finding the critical value and then finding the p-value, they apply to all of Chapter 11. Whether it's a goodness of fit test or an independence test, the process is the same because it uses the same distribution. In the next video, we'll look at a hypothesis test using the chi-square distribution. In this video, we'll run through a chi-square goodness of fit test using Statcrunch. In this example, the big idea is to compare some actual results against what we expect to have seen for different categories. So this is a game where there's a number of games that are played and we're looking for the best of 7 in a series, maybe like the World Series, along with the expected proportions for that number of games. So in this picture right here, we have games played. Sometimes 4 games are played in this best of 7. Sometimes 5 games get played in best of 7, or 6 or 7. And then down at the bottom of the table, we have the expected proportion. So if we're looking at teams of equal abilities, someone has come up with a probability of achieving 4 games in a best of 7 series. So it looks like to have 4 games played, it's a 2 out of 16 chance. If 5 games are played, it's a 4 out of 16 chance, and then 6 or 7 games each have a 5 out of 16 chance of occurring. Now, when the actual series were played, we had 16 contests that ended up with 4 games played. Then we had 20 contests where there were 5 games played, and then 20 and 39. So our goal is to compare this 16, 20, 20, 39 pattern to see if it reasonably fits or doesn't fit with a 2/16, 4/16, 5/16, 5/16 pattern. So you could look at this and say, it looks like there's a lot of 7-game series matches that happen more often than 5 or 6, and 5 or 6 happened equally as often. But the theoretical probability is that there's a very low chance of 4 games, a little bit higher chance of 5, but then 6 and 7 are equal and just a little bit more likely to happen than 5 games. So we're going to see if what actually happened, that's the middle row, agrees with what we expect to happen. So the null hypothesis for these goodness of fit tests is always the observed frequencies agree with the expected proportions. So what we thought would happen and what actually happened are in agreement. And then the alternative is at least one of the observed frequencies does not agree with the expected proportions. So what this means is that if any one of these observed frequencies is wildly different than what you expected with the proportion, it's actually going to throw off everything else. So with these contests, if you get more than, 2/16 turns into 1/8. If you have way more than 1/8 of the games in this first category, you're going to have more or less games in each of the other 3 categories. So one higher is going to bump any of the other categories higher or lower. So that's why we can get away with saying if one of the observed frequencies is off, it's going to push around everything else. If you imagine like a little example, if you have a ball of Play-Doh, you have a fixed amount of Play-Doh, and if you push on one end of the Play-Doh and make it flatter, then another part is going to smush out flatter or get taller. you have the same amount of dough, it just changes shape. So you have the same number of games, they just change shape by being located in different categories. So the null and alternative hypotheses are pretty boring for a goodness of fit test. It's very different than our means and proportions tests that we saw before. All right, I'm going to bring this data into Statcrunch by clicking on the little box and then say open in Statcrunch, and it will. And we have the actual games, the games played. This is kind of like a label for the categories. The actual number of contests, and then the expected proportion in the last column. So those 2/16, 4/16, 5/16 have been turned into decimals. Now to do the goodness of fit test in Statcrunch, we're going to go to the stat button, all the way down to the bottom, goodness of fit, and then we're doing a chi-square test. We just have to tell Statcrunch where to find our data. So observed means where are the observed counts. They are in the actual contests, so that middle column. And then we tell it what are the expected proportions. The expected proportions are there in that label, or in that category, expected proportion. If you have another type of test where all categories are equal, like that dice example that I had shown you in another video, you could just click this box, all cells are equal proportion. Saves you a little bit of time, I suppose. And then you don't have to fill out anything else, you can just push compute. So what we have here in this chi-square output, we have the variables, the observed and expected, and then what they're labeled. We have n, so that's our sample size. It looks like there were 95 games that were played. So our degrees of freedom are 3 because we have 4 categories, and 4 minus 1 is 3. Then we have 8.11. That's our chi-square test statistic. And then lastly, we have the p-value, 0.0438. Another part of this output is the observed count as well as the expected count. So like I showed you in another video, to get expected frequencies, you multiply your sample size, 95, by all of your proportions. So I took 95 and multiplied it by 2/16, and that's how I got 11.875. 95, again the sample size, multiplied by 4/16 is 23.75. A common mistake is that students will take the observed count and multiply it by the proportion, but that's wrong. We want the sample size because you're spreading all of the games around in the 4 categories according to the null hypothesis. So there's not much that we do down here with the observed and expected. We can just visually look at how close or far apart those numbers are. What's more interesting is the p-value, and then we can make a conclusion. So if we go back to this problem here, it said use a 5% significance level to test the claim that the actual number of games fits the distribution indicated of the expected proportions. So if I go back and fill in my chi-square value, that was 3 decimal places, 107. 8.107. Great. P-value is to 4 decimal places, so 0.0438. Great. And then the conclusion of the test. So we had a 5% significance level. The p-value is lower than your level of significance. So the p-value is low, H0 must go. We're going to reject our null hypothesis. So that means that A and C are the options, and then we need to figure out which of those two is correct. So then there is insufficient evidence to warrant rejection of the claim that the actual number of games fit the distribution indicated by the expected proportions, or there is sufficient evidence to warrant rejection of the claim that the actual number of games fit the distribution indicated by the expected proportions. Well, even just halfway into the sentence, you can see that there is sufficient evidence to reject that the data do fit. We're rejecting that because the p-value is small. So it looks like those actual contests don't really follow that proportion that we saw with the expected proportion in that null hypothesis. So let's check. There we go. And we're done. So in that example, we saw an entire goodness of fit test. You'll notice that there's one row of proportions. We had one column of proportions. Goodness of fit tests are like that. You have a number of categories that tend to fit in a row. And I point this out because the next chapter, you have a lot more categories that fit into a table. So you have multiple rows.